On July 15th, 2024, at Cape Canaveral, a seemingly ordinary SpaceX Falcon 9 rocket carried an extraordinary secret into orbit. Hidden among routine satellite deployments was a small, unassuming device that would change space travel forever. The FireStar fusion drive, humanity's first nuclear fusion-powered spacecraft engine. Dr. Sarah Chen, 32, watched the launch from RocketStar Inc.'s Mission Control in New York. As the company's chief propulsion engineer, she had spent the last 6 years developing what many experts considered impossible: a compact fusion reactor that could fit inside a spacecraft and provide both thrust and electrical power for interplanetary missions. The FireStar drive represented a quantum leap beyond conventional rocket technology. While chemical rockets could achieve exhaust velocities of 4 to 5 kilometers per second, Sarah's fusion engine promised exhaust speeds of over 100,000 kilometers per second, about one-third the speed of light. This wasn't just an incremental improvement, it was a complete transformation of what spacecraft could accomplish. The physics behind fusion propulsion was elegantly simple, yet incredibly challenging to implement. Nuclear fusion, the same process that powers the sun, releases enormous amounts of energy when light atomic nuclei combine to form heavier elements. Unlike nuclear fission, which splits heavy atoms and produces dangerous radioactive waste, fusion could be clean and safe when properly controlled. Sarah's breakthrough came from using anitronic fusion, specifically the fusion of boron and hydrogen nuclei. This reaction produced no harmful neutron radiation, making it safe for spacecraft materials and human crews. The process used ordinary water as a hydrogen source, providing both fuel and the basis for generating the high-energy plasma that created thrust. The FireStar drive worked by creating a controlled fusion reaction in a compact magnetic confinement chamber. Powerful magnetic fields compressed and heated the boron-hydrogen plasma to over 100 million degrees Celsius, 6 times hotter than the sun's core. At these extreme temperatures, atomic nuclei overcame their natural electrical repulsion and fused together, releasing tremendous energy. But Sarah's real innovation was in how this energy was converted to thrust. Instead of trying to generate electricity first, like terrestrial fusion power plants attempted to do, the FireStar drive channeled the fusion energy directly into the exhaust stream. High-energy particles from the fusion reaction were magnetically directed through a specialized nozzle, creating thrust with unprecedented efficiency. The test mission, launched in July, was the culmination of 3 years of ground testing and simulation. Sarah's team had built a full-scale prototype in RocketStar's New York facility, demonstrating sustained fusion reactions in a controlled environment. The space test would determine whether the technology could operate reliably in the harsh conditions of space. Initial telemetry from the FireStar drive exceeded all expectations. The engine ignited successfully in orbit and maintained a stable fusion reaction for 72 continuous hours, far longer than any previous fusion experiment in space. Thrust measurements confirmed a 50% improvement in efficiency compared to conventional electric propulsion systems, exactly matching Sarah's theoretical predictions. But the FireStar drive was just the beginning. While RocketStar focused on small-scale propulsion systems for satellites and small spacecraft, other companies were developing fusion engines capable of powering massive interplanetary vessels. Pulsar Fusion, a British company led by CEO Richard Dynon, was building the Sunbird, a fusion-powered spacecraft that could transport 1,000-kilogram payloads to Pluto in just 4 years. Their dual direct fusion drive, DDFD, promised to provide 2 megawatts of electrical power alongside tremendous thrust, enabling scientific missions to the outer solar system that would be impossible with conventional propulsion. The Sunbird represented a completely different approach to fusion propulsion. Instead of the compact, lightweight design of the FireStar drive, Pulsar's system was built around a large, linear fusion reactor that could sustain continuous reactions for years. The reactor used a magnetic field configuration that compressed fusion fuel to the densities required for energy release, while preventing the plasma from touching the reactor walls. Sarah had visited Pulsar's facility in Oxfordshire, England, and been amazed by the scale of their operation. The company had built 2 of the largest space propulsion testing chambers in Europe, capable of simulating the vacuum and radiation environment of deep space. Their test reactors had achieved fusion break-even. the point where the fusion reaction produces more energy than is required to sustain it. The reason we remain so focused on fusion, Dynan had explained during Sarah's visit, is because as our satellites and payloads get bigger and we start going into deep space missions, we have a problem. Solar intensity starts to fade away, so we need new power sources. The mathematics of space travel supported Dynan's argument. Solar power decreased with the square of distance from the Sun. At Jupiter's orbit, solar panels received only 4% of the power they would at Earth's distance. At Pluto, solar intensity was less than 0.1% of Earth levels, completely inadequate for powering large spacecraft or scientific instruments. Fusion changed this equation entirely. A fusion-powered spacecraft carried its own star, providing virtually unlimited energy anywhere in the solar system. The Sunbird's 2-megawatt power output could support massive scientific instruments, high-bandwidth communications, and even manufacturing facilities on distant worlds. The implications were staggering. Traditional missions to the outer solar system took decades and required careful gravitational slingshot maneuvers to build up speed. The Voyager probes, launched in 1977, took 12 years to reach Neptune. New Horizons, the fastest spacecraft ever launched, took 9.5 years to reach Pluto. Fusion propulsion could reduce these journey times by an order of magnitude. Pulsar's calculations showed that a Sunbird-class vessel could reach Jupiter in 18 months, Saturn in 2.5 years, and Pluto in 4 years. More importantly, these spacecraft could carry massive payloads and provide their own power for extensive scientific operations upon arrival. By 2025, the technology was advancing rapidly. NASA's Innovative Advanced Concepts (IAC) program had awarded grants to multiple fusion propulsion projects. Helicity Space, led by Dr. Ryan Weed, was developing a constellation of fusion-powered spacecraft for exploring the heliosphere, the boundary region where the solar wind meets interstellar space. Helicity's approach used a different fusion reaction altogether. Their Helicity drive employed deuterium-tritium fusion, the easiest fusion reaction to achieve, but one that produced neutron radiation. They solved the radiation problem by using the neutrons to heat a separate propellant stream, avoiding direct exposure of the spacecraft to radiation while achieving extremely high exhaust velocities. Sarah was particularly intrigued by NASA's own fusion propulsion research. The space agency was developing a fusion-driven rocket, FDR, that used a revolutionary technique called magneto-inertial fusion. The system compressed fusion fuel using powerful magnetic fields generated by imploding metal liners, achieving fusion conditions in a relatively compact device. The FDR promised exhaust velocities exceeding 30 kilometers per second with specific power levels around 1 kilowatt per kilogram, minus performance characteristics that would enable rapid transit throughout the solar system. NASA's projections showed that an FDR-powered spacecraft could reach Mars in just 30 days, transforming the red planet from a distant destination requiring years of travel into a routine destination accessible within a month. But fusion propulsion wasn't just about speed. The high power output of fusion reactors enabled entirely new types of space missions. Traditional spacecraft were severely power limited, restricting the size and capability of their scientific instruments and communication systems. A fusion-powered spacecraft could operate massive radar systems for subsurface exploration, particle accelerators for in-situ materials analysis, and high-powered transmitters capable of streaming high-definition video from anywhere in the solar system. The Sunbird's 2-megawatt power output was comparable to a small terrestrial power plant, enough to run an entire research facility on another world. The commercial implications were equally revolutionary. Asteroid mining companies had long struggled with the economics of space-based resource extraction, the massive energy requirements for processing asteroid materials, and the long transit times to profitable asteroids made most projects economically unfeasible. Fusion propulsion changed this calculus entirely. A fusion-powered mining vessel could travel to the asteroid belt in months rather than years, carry massive processing equipment, and provide abundant power for extraction and refining operations. The same vessel could then return to Earth with processed materials in a fraction of the time required by conventional spacecraft. Sarah's company, FireStar, was already developing second-generation fusion drives optimized for commercial applications. The FireStar 2 would provide 10 times the power output of the original design, while maintaining the compact form factor that made it suitable for relatively small spacecraft. But the real breakthrough came in late 2025, when Princeton Satellite Systems announced a partnership with Pulsar Fusion to develop AI-assisted fusion reactor control systems. The challenge with fusion reactions had always been maintaining the precise conditions required for sustained energy release. The plasma had to be held at exactly the right temperature, density, and confinement time, parameters that could change microsecond by microsecond. Artificial intelligence offered a solution. Machine learning algorithms could monitor thousands of plasma parameters simultaneously and make real-time adjustments faster than any human operator. The AI system learned from each fusion pulse, gradually optimizing the reactor's performance and extending the duration of stable reactions. The results exceeded everyone's expectations. AI-controlled fusion reactors achieved continuous operation periods, measured in months rather than minutes. Fuel efficiency improved by 300%, and power output became remarkably stable and predictable. For the first time, fusion propulsion became truly practical for long-duration space missions. Sarah was selected to lead the first crewed mission, powered by fusion propulsion. The Prometheus mission would carry a crew of 6 to Mars using a Pulsar Fusion Sunbird drive, demonstrating the technology's readiness for human spaceflight. Unlike previous Mars missions that required careful launch windows and followed efficient but slow transfer orbits, Prometheus could launch at any time and reach Mars in just 45 days by operating well below its maximum theoretical exhaust velocity for safety and comfort. The spacecraft design was unlike anything previously built. The Prometheus measured 150 meters long, with the fusion reactor housed in a heavily shielded compartment at one end and the crew habitat at the other. The distance was necessary to protect the crew from the intense magnetic fields and residual radiation produced by the fusion process. The crew habitat itself was revolutionary. With abundant power available from the fusion reactor, the spacecraft could provide Earth-normal atmospheric pressure, gravity generated by rotation, and extensive recreational facilities. The journey to Mars would be comfortable rather than the cramped, stressful endurance test of previous missions. Sarah's role as chief propulsion engineer made her responsible for the fusion drive's operation throughout the mission. She would monitor the reactor's performance, make real-time adjustments to thrust levels, and ensure the engines continued safe operation during the 45-day transit. The Prometheus mission launched on March 15, 2027, from Kennedy Space Center. Unlike traditional rockets that struggled to escape Earth's gravity well, the fusion-powered spacecraft ignited its drive while still in Earth orbit and accelerated continuously throughout the journey to Mars. The sensation of acceleration was unlike anything experienced on previous space missions. Instead of the brief, intense thrust of chemical rockets followed by months of weightless coasting, Prometheus provided steady, gentle acceleration that created artificial gravity throughout the spacecraft. The crew could walk normally, eat regular meals, and exercise using conventional equipment. Sarah monitored the fusion reactor from the engineering station, watching as boron-hydrogen fuel combined at temperatures exceeding 150 million degrees Celsius. The magnetic confinement system held the fusion plasma in a perfect toroidal shape, preventing the star-hot material from touching the reactor walls. Real-time telemetry showed reactor performance within optimal parameters. Fusion efficiency remained above 85% throughout the journey, with the reactor consuming less than 200 kilograms of fuel to transport the entire 450-ton spacecraft from Earth to Mars. By comparison, a chemical rocket would have required over 2,000 tons of propellant for the same mission. The journey provided an unprecedented opportunity to test fusion propulsion under real operating conditions. Sarah's team collected thousands of hours of performance data, documenting how the reactor responded to course corrections, throttle changes, and the varying magnetic field environments encountered during the transit. One of the most remarkable discoveries was the reactor's stability. Unlike the brief, explosive fusion reactions achieved in laboratory experiments, the Sunbird drive maintained steady output for weeks at a time. The AI control system continuously optimized plasma conditions, achieving fusion burn durations that would have been impossible with manual control. The Prometheus mission arrived at Mars on April 29, 2027, just 45 days after launch from Earth. The landing was as revolutionary as the journey itself. Instead of the complex aerobraking maneuvers required by conventional spacecraft, Prometheus simply reversed its thrust and decelerated directly into Mars' orbit, then descended to the surface using fusion-powered retropropulsion. The mission's success triggered a revolution in space exploration. NASA immediately approved funding for a fleet of fusion-powered spacecraft, each optimized for different mission profiles. The Icarus class would focus on inner solar system exploration, carrying large scientific payloads to Venus and Mercury. The Odyssey class would specialize in outer solar system missions, reaching Jupiter, Saturn, and beyond, with unprecedented speed and capability. Commercial space companies rushed to develop their own fusion propulsion systems. SpaceX announced plans for a fusion-powered version of Starship, capable of reaching Mars in 3 weeks. Blue Origin revealed designs for fusion-powered space stations that could be positioned anywhere in the solar system. Virgin Galactic proposed fusion-powered space tourism flights to Jupiter's moons. The economic impact was immediate and profound. Fusion propulsion reduced the cost per kilogram of delivering payloads to Mars from $50,000 to less than $500. Asteroid mining became economically viable overnight, with fusion-powered vessels capable of reaching profitable asteroids in months and returning with processed materials. The outer solar system, previously accessible only to robotic probes after decades-long journeys, became a routine destination for crewed missions. Research stations were established on Europa, Enceladus, and Titan, powered by fusion reactors and supplied by regular cargo runs from Earth. Sarah found herself at the center of humanity's expansion into the solar system. As director of fusion propulsion development for the newly formed International Space Agency, she oversaw the design and construction of increasingly powerful fusion drives. The latest generation could accelerate 10,000-ton spacecraft to velocities approaching 1% of light speed. But perhaps the most significant impact of fusion propulsion was cultural. For the first time in human history, space was not a hostile frontier requiring years of preparation and risk for brief visits. It had become an accessible environment where humans could live, work, and thrive. Standing on the observation deck of Titan Station in 2030, Sarah watched fusion-powered cargo ships arriving daily from Earth, Jupiter, and the asteroid belt. Each ship carried settlers, supplies, and equipment for humanity's growing presence throughout the solar system. What had once been a journey requiring decades now took mere months. Titan Station itself was a marvel of fusion-powered engineering. Built in orbit around Saturn's largest moon, the station housed 5,000 researchers and support staff studying the complex chemistry of Titan's atmosphere and surface. The station's fusion reactors provided power for massive atmospheric processing equipment, advanced laboratories, and even recreational facilities that rivaled Earth-based resorts. The scientific discoveries enabled by fusion propulsion had revolutionized understanding of the solar system. Europa Station, built on Jupiter's ice-covered moon, had confirmed the existence of complex organic chemistry in the moon's subsurface ocean. Enceladus Base had discovered active volcanic chemistry in Saturn's small icy moon. Each discovery was enabled by the massive power requirements of deep drilling and analysis equipment that only fusion reactors could provide. Sarah's role had evolved from engineer to administrator as humanity's fusion-powered expansion accelerated. As director of the Solar System Transportation Authority, she oversaw a fleet of over 200 fusion-powered spacecraft operating throughout the solar system. Each ship represented years of development and billions of dollars in investment, but the economic returns were enormous. Asteroid mining had become the solar system's most profitable industry. Fusion-powered mining ships could reach the most valuable asteroids in the belt and return with processed materials in less than 2 years. A single metallic asteroid contained more platinum, gold, and rare earth elements than had ever been mined on Earth. The abundance of space-based materials had triggered an economic revolution, making previously expensive technologies affordable for everyone. The rings of Saturn hung in the black sky above, beautiful and ethereal in the light of the distant sun. But they were no longer unreachably distant. Fusion propulsion had brought them within easy reach, transforming the entire solar system into humanity's backyard. Sarah often thought about her parents, who had passed away in 2029, just as the fusion age was beginning. They had immigrated to America dreaming of opportunities for their children that didn't exist in their homeland. Sarah had exceeded even their most ambitious dreams, becoming the architect of humanity's expansion across the solar system. The cultural impact of fusion propulsion extended far beyond engineering and science. A generation of children was growing up in space, born on stations and bases throughout the solar system. These space-born humans thought differently about distance, resources, and the relationship between Earth and the cosmos. To them, Jupiter was a weekend destination, not an impossible dream. Sarah often reflected on how quickly everything had changed. In just 6 years, fusion propulsion had evolved from an experimental laboratory curiosity to the foundation of human civilization's expansion across the solar system. The first starships had been built and were already carrying humans to destinations that had been science fiction just a decade earlier. The nuclear fire that powered the stars had been tamed and harnessed for human exploration. Sarah Chen, the propulsion engineer who had made it possible, had given humanity the key to the cosmos, engines that burned with the power of stars themselves, carrying human dreams to worlds beyond imagination.